जीमेल तो अनुसार
जीमेल पे कर लगा कैमरा नॉट फोन नो कैमरा फोन
మనం ఎడుగుచ్చిన వచ్చిన వాళ్ళు అడ్మిట్ పడతాం నేను ఈ పనిలో ఉంటాను అస్సలు డిస్టర్బ్ చేయదు
నేను అడ్మిట్ పడ్డాను పని
అంతే ఇంకేం చేయదు
నా ఫోటో కనపడుతుంది
వేరే పని
పంపిస్తాను
ఏ సార్ దుర్గాప్రసాద్ సార్ పంపించేది ఏంటి
దీంట్లో వాట్సాప్ డిపి ఉంది
తీసి పెట్టుకో నువ్వు తీయలేవా
అదే లేదు
వాట్సాప్
సార్
కాదు సార్ కాలేజ్ గ్రూప్ ఉందా కాలేజ్ గ్రూప్ పెట్టారు లైవ్ అట్లా వస్తూ ఉంటుంది యూట్యూబ్లో యూట్యూబ్లో ప్రస్తుతం కాలేజీ పేరు యూట్యూబ్లో లైవ్ వస్తుంది అదేనా కాలేజ్ గురించి నేను స్కూల్ వేస్తున్నా యూట్యూబ్లో వస్తుంది స్లోగా ఉంది ఒకసారి జస్ట్ క్లిక్ అంతే అట్లా జెంట్లుగా నేను ఆల్రెడీ గ్రూప్లో వీడియో వెళ్తుంది వీడియో కూడా ఆడుతుంది బాబు 10:15 ఎవరు ఫస్ట్ స్పీచ్ ఏది ఆమె
అయినా
10-12 అయింది రాజేష్ ఆన్ చేయాలి అడ్మిట్ రాయేష్ బిజిమాల్ మేడం స్పీచ్ స్టార్ట్ చేయాలి
సార్ అదే కదా.
బిజిమాల్ మేడం స్పీచ్ స్టార్ట్ చేయాలి ఎక్కడున్నారు
మేడం అక్కడ
ప్రిన్సిపల్ ఆఫీస్ దగ్గరికి వెళ్ళి ఆమె స్పీచ్ స్టార్ట్ చేయాలంటే ప్రిన్సిపల్స్ వాళ్ళు ఎవరైనా సెక్రటరీ గారు వస్తుంది go. Go to meeting. Meet that rule. ఫోటో తీసుకుందాన్ని ఫోటో గ్రూప్ లో పెట్టు లైవ్ 10:16 అయింది ఆవిడ స్పీచ్ వాళ్ళ బిగిన్ చేసేసారు ఫస్ట్ స్పీకర్ సెక్రటరీ గారు 10:15 ఈజ్ లైవ్ సెక్రటరీ గారు లేదు 10:30 కి కదా ఫస్ట్ డైరెక్టర్ గారు తర్వాత ప్రిన్సిపల్ స్పీకర్ హాయ్ ఎస్బీఆర్ వస్తున్నట్టు రోజు అదే యూట్యూబ్ లో డెస్క్టాప్ మీద ఏదో ఓపెన్ చేశారు మీరేం మీటింగ్ స్టార్ట్ చేయరా ఖాళీ అంటే ఖాళీ నేను కలపొద్దు నేను ప్రోగ్రామ్ లో ఉన్నాను రాయల్స్ వస్తున్నాడు సాయి మేడం గారు 10:15 స్టార్ట్ చేయాలి స్టార్ట్ చేయాలి టైం దాటిపోయింది అదే స్టార్ట్ అయిపోయింది మేడం ఆల్ ద బెస్ట్ గుడ్ గా అంటే మనకి యాక్చువల్ 10:30కి అవును ఈరోజు 10:30కి కన్నదే మేడం గారు అడ్మిట్ కొట్టలేదా ఏమన్నా ఆస్కింగ్ టు జాయిన్ ఏంటి? అసలు క్యాండిడేట్ జాయిన్ అవ్వలేదు. ఆ? ఏం పెట్టారు మీరు? మేడం మేడం మీరు ఇక్కడి నుంచి మాట్లాడేసేయండి.
ఇక్కడ లేకపోతే
ఆ.
పేపర్స్ తెచ్చుకొని అడ్మిట్ చేశాను.
చేశారా మేడం? అడ్మిట్ అయ్యారండి, కూర్చోండి కూర్చోండి. అడ్మిట్ అయ్యారండి, కూర్చోండి. యూట్యూబ్లో తెలియదు.
అలాగే అదే
అడ్మిట్ అయ్యారు. ఓకే, ఒక్క నిమిషం. మేడం
మాట్లాడచ్చు.
Dear all, warm greetings from Cinema College of Engineering in Patna. It gives me great pleasure to extend you all a very warm welcome on behalf of National Engineering Department, Pottaniramlu Chalwadi Mallikarjunarao College of Engineering and Technology, Vijayawada. This is Dr. Bindu Madhavi, Professor in Physics. First of all, on Dr. Rudeshekar Manna to this session. I specifically thankful to him because working as an assistant professor in the Department of Physics in Indian Institute of Technology, Tirupati. Before joining IIT Tirupati in 2017, he also worked as postdoctoral research associate, Augsburg University, Germany, during the year 2014 to 2017, and also at Goethe University, Frankfurt, Germany, during 2012 to 2014. Dr. Rudhashekar Manna received his PhD in the year 2012 from Goethe University, Frankfurt, Germany, for his work in thermal expansion studies on low-dimensional cathode quantum magnets under the guidance of Professor Dr. Michael Lang. Dr. Rudhashekar Manna is the member of the American Physical Society. He also is an active member of Goethe Graduate Academy, Goethe University, Frankfurt, Germany, from 2018 to 2014. He was the successful candidate of JSPS Fellowship in 2014. He has delivered 42 talks, both at national and international levels. We are all very glad to have you, Dr. Rudhashekar Manna, here today to discuss a topic about a journey through low temperature physics with various exotic cases. Before I invite Dr. Rudhashekar Manna, I would like to invite my principal, Dr. K. Ramakrishna, to speak few words about this faculty development program. Sir, principal sir, are you there? Dear sir? Yes.
Yeah, hello, madam.
Sir, welcome, sir.
Good morning. Thanks for the welcome. Good morning, Dr. Madhavi. Thanks for the invitation. And I'm glad to be part and parcel of this conference. I appreciate for taking such a wonderful topic for the 3 days conference, moving the faculty, students and researchers, mastering science into the technological domain. It's quite surprising and it's a challenging task that you have taken up. I extend my appreciation to you and your team members. And I'm also glad that as many as about 2,000, faculty members, research scholars, and students have, enthusiastically registered to, take themselves with their science into technology. I'm glad and extend up my appreciations once again. And the management members, as you know, are quite busy with their activities, could not attend, and in their absence, I welcome their blessings to this 3 days conference. And I extend my congratulations to all the team members, each and every one who contributed directly for organizing and facilitating this program. And I'm a little bit surprised to see this science, technology movement. I'm in between in engineering. Sometimes I get a doubt if I'm permitted to talk a couple of minutes. The Newtonian theorem, Newton's mechanics, and then the Einstein's theory of relativity, because I have been teaching these courses to the UG and PG students for a long time. I get a major question that I think you can also, if time permits, focus on doing some research on this. The quantum gravity is always troubling me. That's not defined, meeting the Einstein's equivalence and the Newtonian physics. As you know, all the objects fall under the influence of the gravity, as with the Newton, maybe in the 19th century, 17th, I don't know, I don't remember, but Einstein says that this is not due to gravity, this is due to the curvature of this space and time, of the matter and the energy, but these two are contradictory. When I teach this quantum physics and the theory of relativity of Einstein, my students get wonder to listen to me. Professor is giving two contradictory statements. One at the micro level Newtonian physics, it's at larger level at cosmos level. He's talking about Einstein's theory of relativity. How do we define this quantum gravity? Is a troubling question. I get afraid to go to UGPG classes. I think you can throw some light on this. I take this opportunity to welcome Dr. Rudra Shekhar Manna, Assistant Professor, Department of Physics, IIT Tirupati. I welcome you, sir. And I would also like to, enhance my knowledge on the low temperature of physics with various exotic phrases that we are going to talk about. And I strongly believe that these 2,000 members will pay utmost attention to enhance their capability and profundity of their mastery in science, to take them to technology. That's a good effort. And at the end, I would like to see that all these 2,000 members get benefited and a measurable outcome is going to be generated. That's what I expect from the Institute. I wish this program a grand success, and I congratulate once again the entire team that has come forward to stand up to take this 3-day event. And I am so thankful to my management for its contribution in all directions. And I wish all of you a grand success. I would like to see you after 3 days and then see the research outcomes or whatever you achieve, the excerpts I would like to share. I wish you all the best, and thank you so much for giving me this opportunity. All the best. Good luck to you all.
Thank you, sir. Thank you very much, Principal Sir, for your words. And sir, the field of science and particularly the field of quantum mechanics, quantum physics is like that, sir. It is a very surprising. All the contradictory concepts which are dealt with the classical mechanics are well explained by quantum mechanics, sir. Anyhow, we also as faculty are very much interested and astonished looking into the quantum theory, sir. Thank you very much, sir, your presentation. Sir, Dr. Rudra Shekhar Manna, sir, before you start your presentation, just I would like to give some instructions to the candidates. Okay, sir?
Okay.
Dear participants,
Please mute your audio and
please
video
mute your audio and video just for avoiding
just for
disturbance
please
during
do
the
not
session.
share anything on
Okay. Next, please do
do
not
not
share
share
anything
anything
on the
on the
screen.
chat box
You can post your
after
questions in the chat
the
box after the
please
presentation of the
avoid
speaker.
writing
Please do
on chat
avoid
box
writing on chat box and sharing your screen. Thank you very much. The feedback link will be posted at the end of the session. Please cooperate and all of you switch off your video and mute your audio. Thank you. Now, for those who have joined us now, I again welcome all the participants, and I would like to introduce today's presenter, Dr. Rudra Shekhar Manna. Sir, dear Rudra Shekhar Manna, please you introduce your presentation. So please start your presentation. Thank you.
Okay, thank you very much. Good morning, everybody. Am I audible?
Yes, sir. You are audible.
Yeah, good, that's fine. Good morning, everyone. So before I start, first, I would like to thank you and first the director sir and the principal sir for your kind words, and specifically Professor Bindu Madhavi. So first he contacted me actually, and it's a surprise actually. This time we are all looking for all these virtual seminars, and also we are doing regularly virtual teaching and all these things. Then although I didn't know about this college, but initially I responded because that how we should do actually. We should also we have a program called outreach program where we try to go or try to coordinate with other colleges or different schools to encourage students all across the country. So that is also a privilege for me. And thank you very much for choosing me or selecting me for this seminar. And so I hope all of you are staying safe and taking care of yourself and also your families and also your neighbors or surroundings. And so with that, I would like to thank you again for the nice program where you, although it's called a faculty development program as far as I understood, but it somehow connects with science and engineering. And I have also seen the programs. There are people you invited for science background, also engineering background. So there is some very good mixture to that. So at the end, I hope participants will be benefited. And personal to my talk, you can also ask me questions at the end. Normally, I like to have questions in between the talks, but here, since it's a virtual thing, so it's better not to disturb others and that way to talk. So you can ask the questions really at the end, or you can post me questions by emails or telephones or whatever way you like to talk. So now let me start with my presentation now.
233 watching. YouTube 233, 235 watching.
So the screen is visible now. Is it visible? Can you some comment? The screen is visible.
Yes, sir.
Okay, good.
Yes.
Good. Thank you very much. So here, so I chose a topic which is actually my field of research, which I'm doing more than a decade. And so basically, when you talk about first of all, you could ask why we go to low temperature. The first thing comes to your mind, okay, everything is at room temperature. We do different things at room temperature, and different whatever we apply or the application point of view, we do everything at room temperature. Then the question comes, why low temperature? Why it's so special? And so before that, we should know that what does it mean actually, the low temperature, that I will explain, and how low one could go, and what is our limit, and what is the total temperature spectrum, so to say, and why it is interesting. And but if you just see which I will talk about, but before that I brief you that there are some very exotic phases, and which normally we don't expect at room temperature. Those things, and as a huge practical applications, and there one can be benefited a lot. If you can somehow scale up the temperature, you can modify, you can tune those systems somehow to the room temperature. So that is the goal. And so anyway, I'm from Department of Physics at Tirupati, and let me go through a little bit where we are located. Actually, I mean, most of you know where Tirupati is because of the famous temple, but still, if you look at the screen, so where we are, close to Chennai, so it is like 130-40 kilometers away from Chennai, and where we are presently located, actually, we started our operation in 2015, and where it's a third generation of IIT. As you know, the first generation of IIT is older IITs like Kanpur, Bombay, Roorkee, and Madras, and all these things. And then later on, second generation came like IIT Hyderabad and Indore and Gandhinagar and all these things. And the third stage, we just started in 2015, also branch of IITs for 3G IITs like IIT Tirupati, Palakkad, Goa, Dharwad, and Bhilahi. So here we are. So initially to start the operation, we had some engineering college also in Tirupati, close to Renigunta railway station. Most of you are familiar with this railway station because you come to Balaji Temple, and that is where we are located. But parallelly, we are having a permanent campus, which is little far from here, which is called little 20 kilometers away, or from the railway station maybe 12 or 10 kilometers away. Direction Jamnagar is called Eripedu. It's a village, and where we have actually government of Andhra Pradesh or the state government, the central government, and we have 530 acres land here, and the beautiful hills, and where we have also some operation already started. Students, all students, roughly 1,000 students are staying in the campus, roughly the corner of 30 acres land, which is called the transit campus. And this is how it looks like, but in reality it looks like this one. You can see it's an aerial view, and where we have all the hostel students are staying. We have laboratories and lecture halls, and we have also indoor stadium and also dining hall. At present, there is actually nobody staying there because of this pandemic situation. And what we have right now, we have 5 engineering departments. One is this computer science, electrical engineering, mechanical engineering, civil engineering, and chemical engineering, and 3 science departments: physics, chemistry, and mathematics, and 1 humanities and social science (HSS), where it comes to like literature and economics, philosophy, and all these things. And particularly the physics department, as we are new, so we have already 6 regular faculties, and we have a couple of PG students who already started their work, and some more yet to come. I mean, when these things are over, then we also are recruiting more students. And the field of area at present, what we are interested in to, or so to say, thrust areas in physics, quantum matter physics, both in theory and experiment, and also the atomic and molecular physics. We have also a group of people, faculties, which are also interested in. And so altogether we have 100 faculty members at this moment, and roughly 1,000 students, including UG, mostly undergrad, who comes with the JE rank. And then we have PG students, and we have PhD, and so on, and some master students as well. So anyways, to start with the topic, now let me brief you with the outline what I am going to talk about. And the moment we change the temperature, as I mentioned already, so then we have little phase changes. So in a material, we have it goes from one phase to another phase, and this is sometimes called as phase transition. And I give you a very common example which you know already, but try to go a little bit more detail what is the physics there, and why this temperature is important. Not only temperature, there are other parameters also important, like you can have pressure, and we can have magnetic field if a magnetic system. And then since this topic is very vast, so then I will focus mostly a couple of phase transitions where we can go to like superfluid. It's a beautiful transition which I will tell you, and also the superconducting phase. Fascinating name. This is more than 100 years research that people are doing, and I will also like to tell you what are those phases and what are the importance to our let's say community or to the society, what will be beneficial. And then I will also talk about a bit of magnetic phase transition, where different magnets are there, what's the origin of this magnetic phase transition, what are the different phases, how we can tune. And while going through all these topics, I will also cover some experimental techniques, how people have developed over the years, and especially I will mention some of the expertise which our group or personally I worked over the years. And these are very special and why they are interesting. Okay, to start with the phase transition. So let us start. So first, we know all people we know about the water. Very good example we use every day. It's day-to-day life. So what we see the water, we have different states. So how we can change this one? So you can have a liquid here to drink, and then you can, if you just boil the water when it's 100 degree or something, then you can get a gas. Then if you can also go to let's say go to northern India, or you can go to abroad in winter, or sometimes you can get also ice when the temperature is changing. So that means the same substance or same material you can see in different forms. and based on the different parameters, basically temperature. And you can think other way also, like every day we have at home, we use, or most of us, we use pressure cooker, which is a very good thing. That means you can use pressure also as a medium. Then you know, if you apply pressure like pressure cooker, it cooks faster. That means the boiling point decreases. Then you can also go to a different phase quicker. So that means these parameters like temperature, pressure even, so that those help to go to a new phase. And that's why in the water, if you can see, so this is a phase diagram. So that means when you are a phase, then there should be a phase diagram. This is y-axis, it's talking about pressure, and x-axis is talking about temperature. And then now you can see that this is in degrees centigrade. So that means you have a different temperatures, and then different pressure. And the pressure units are a little bit. There are different pressure scales, so that can be a little bit confusing. But before I want to make a diagram, so like 1 Pascal, normally you get a 10 power minus 5 bar, or you can think of like when you talk about 1 atmospheric pressure, and which is also equivalent to 1 bar, or that is equivalent to 760 per torr. So that means one can immediately cross check how much pressure it is. And to give you some example, let's say in our regular bicycle or in football or in your scooter or any vehicle, the pressure of inside may be of the order of 4 to 6 bar. So in that way you can think of how much pressure you need to tune from one phase to another. And some material, it depends actually what you work with that. But here in the phase diagram, so what it is interesting. So you can have different phases. So there is the boundary. So you can have water, but if you change the pressure and temperature accordingly, then you are also different regions. That shows different color code here. You can have an ice region, but you can have water also in the region. So based on the temperature and pressure, then you can also do the experiment. And there are interesting points on that. There you can see there are certain points which we know from our school days called triple point. So what does it mean? So that means those points were actually all phases somehow coexist. So that means you can think that there is you can think one point where all phases they coexist, and then people try to understand what is the nature, what is the property of this particular point. Because this is very special points, and or while crossing the boundary, how you cross the boundary. Like you come from this water to, let's say, water vapor. So how you cross the boundary? So then comes also the physics called it's a phase transition. That means you come from one phase to another phase, and by means of some transition, and that's driven by the temperature, pressure. And those transition also, how do you come? That is, if you do mathematics or physics, that is called a phase transition. That means fast order phase transition, or can be a second order phase transition. That means sometimes you can go to a smooth, that the fast derivative goes discontinuous. Now, all these things you can also think in terms of a thermodynamics, because you are dealing with pressure, temperature, and volume. Then you can do thermodynamics. You can try to understand different properties. Or there is also one point called critical point. So that means your phase transition line goes along, and some point suddenly it vanishes, or vanishes after one point. There is point, and there is some special feature. And this is very interesting topics, and you can see already the Nobel Prize was given in 1982. Because of this critical study, people can do also theory and experiment to understand, and they have a very peculiar behavior. I'm not going to very detail of this peculiar behavior, but these are very interesting, and you can imagine there are a couple of physics for this. Now, according to the Russian physicist, also Lev Landau, also got Nobel Prize. And there he pointed out that time, so he gave a theory that every phase transition you should have an order parameter. So order parameter what? So you have some order phase, and then you come from one phase to another phase. So that means what is the microscopic origin to those particular phase transition. And for example, water you can understand easily what should be the order parameter, and then you can think of this the density. So that means if you have a material, if it's highly dense, then you can think of your solid. And the density nothing but your distance between the atoms basically. So that means if you are in the water phase, then how the density is changing, or you can come to the gas phase or in the water vapor phase, then the density is also changing. So that is the microscopic origin, what really drives basically, what parameters. So pressure, temperature is the tuning parameters, but what are parameters? What is the microscopic origin which drives from one to another? And this is one type of phase transition. There are another type of phase transition which I'll go in subsequent slides. So now coming back to temperature, so let me brief you temperature to give you to understand where we are and how the temperature scale varies. Now this temperature scales in the y-axis is given in the Kelvin scale. So to give you those, I think everybody is familiar here. So the 0 degree centigrade, and I have a special intention why calling Kelvin scale. I'll tell you later. But the idea is that so 0 degree centigrade is 273.15 Kelvin. So that means the moment you say close to, let's say, 0 Kelvin, or that means you are going to minus 270 degree, and which is the lowest temperature possible. Now, if you see the highest temperature, which is of the order of 10 power 9, this is the order of 9 here, 10 power 9, which is normally the temperature what we expect or what we have in the hottest star or maybe the center of sun. It's so hot here. Now, there is also range. I go to the somewhere in between where you can say where the chemical energy or some of the surface of the sun. Surface of the sun. This is the core center of the sun, 10 power 7, 8 or 9, and the surface of the sun which is lower, so which is 10 power 4 Kelvin. So which is of the order of power 4, which is also quite a lot. That's why we get sunset here, still very hot. And if you just go back like room temperature, that means roughly you can think 30 degree centigrade, which is room temperature, which is of the order of 300 Kelvin. Room temperature, which you have normal room temperature, because which every things which you operate of the order of within the temperature. So there you can see the temperature of the order of here. So 300 Kelvin means this is 10 power 1, 10. And that is 10 power 2, that means 100. And this is somehow here, maybe 300, somehow maybe here, where the origin of life or all these things. Now coming back to then our universe also has temperature of 3 Kelvin. And if you come to this liquid helium or liquid nitrogen, which you know, liquid nitrogen has a temperature also of the order of 77 Kelvin. And that is also roughly of the order of minus 250 centigrade, roughly also here. Now you come closer, and people try to also reach within the lower temperature. And one of the ideas that just now also at the beginning, our principals had also mentioned that the quantum physics, and here also very much important that why the classical physics it breaks down also, because the classical physics sometimes mostly driven the thermal fluctuations and all these things, and there a lot of quantum phenomena occurs when you go to even lower temperature. That is mostly driven by quantum phenomena, because thermal fluctuation is almost close to zero. And there we go to 10 power, you see, you can go to even lab 10 power minus 9 or nano Kelvin. Sometimes we do with the laser cooling and all these things, where the atoms there maybe they try to trap, it's called laser trapping or cooling. They go to really nano Kelvin range where the motion is really very slow. And then you can tune with the lasers in different directions, then you can trap and you can get the image and you can study physics. So in that way, one can try to understand what is the real true ground state or the real nature of certain material or certain atom, and to do the statistics. Because when it's high temperature, then we don't know, because they are very much chaotic. You look at the theory, gases and all, they are very much chaotic. Then we don't have, let's say, proper idea of how they behave. I mean, we can still do a lot of statistics and all these things. But if you really go to the lowest temperature, then we really know what is the ground state. Now, as you know, why I mentioned this Kelvin scale, because that is 10 power minus 9. Basically, we are going close to the zero. Because the third law of thermodynamics, which states that we never can reach the 0 Kelvin. So, but we can still really go to very close to the 0 Kelvin. And here there is a nomenclature which we use, especially at low temperature. That means when we are below low temperature, T less than 300 Kelvin, that means below room temperature, low temperature. And below 4 Kelvin, T less than we can call it very very low temperature. That is our nomenclature. Just we have to PPT is not visible.
ఆయన షేరింగ్ ఆపేసాడు. ఇప్పుడు షేర్ చేస్తాను.
The PPT is visible now, madam?
Yes, sir. Now it is visible, sir. Now it is visible.
Okay. I just removed the off screen mode. Full screen I do. It's fine. So that means we are in the. So sorry for the disturbance. Those of you who didn't follow. So I was just here giving a range of temperature and where different phases can be or different temperature scales where and what is the importance of this. The temperature scale, and then we define what is we cannot go to T equal to 0 Kelvin because of the violation of third law of thermodynamics, but we can go to that particular temperature, close to that temperature, and do a lot of things. And now the question is that okay, the moment you go to that particular low temperature, then what to be done, because the outside is room temperature and you want to do some experiment or something at low temperature, then you have to somehow decouple the system. So and those kind of instrument is called cryostats. That means where you can do all the experiment inside is very cold, but outside is warm as usual. So these are called cryostats, and I will give you some also examples and some pictures how one does all these experiments. Now coming back to the different phases, so initially I talked about a very common phenomena which is called the water, basically the different phase conditions. Now coming back to the different kind of phases, now we talk about helium. It's a beautiful thing in helium, because helium, as you know, it's a very light element, and in our atmosphere it is very rare to get. But the helium, when first discovered, actually it is they try to liquefy, and the temperature was 4.2 Kelvin. And if you want to do a low temperature measurements, you need to have this helium. But helium is pretty expensive. I will tell you in the subsequent slides how expensive they are. But they can also, you can have also helium. You have normally gas. And why it is so expensive? The reason is that outside you have very less percentage of helium, and then you have to somehow store those heliums and you have to liquefy. And liquefy means nothing but you can give pressure, and that is again a pressure and temperature phase diagram. So liquid helium also can have different phases. Only the thing different is that here the pressure and temperature ranges are different, because now you can say now after that I will talk about in the Kelvin scale, because the temperature is very very low. And you can have also gas phase, you can have a normal liquid phase.
Sir, some disturbance is that we are hearing two voices.
Is it fine now?
No, sir. Some background voices coming.
From my side, I'm sorry.
No, sir. Someone listening.
Okay, I think I request all the participants to mute your microphone so that the disturbance background noise is a bit less, so that everybody can hear.
So here all the participants are muted their voices, but someone in different side, I think it is the host side. It's not your side, that is the host side.
Okay, host side, please take care. But from my side, I don't hear also the disturbance. So they will take care anyway.
Sir, excuse me, here everything is okay. I think it is the problem with the internet or something else. We are also getting the same sound here, but everyone is muted their phones.
Okay.
So let us be patient and listen to the speaker, please. And sir, you can proceed.
Okay, thank you. So here the beautiful thing is the helium. Then you may ask, okay, why such a low temperature and all these things? Why you are talking in this particular thing? There is one phrase you can see in the left hand side, this corner. It's called superfluid, and that's a beautiful phenomenon when you talk about the Newtonian physics and all these things. You know the first law of the Newton, which tells okay, you have this friction force. That means at some point you just throw a ball, then at some point it stops because of friction. But here you see, and you can talk about also in terms of viscosity, where the viscous liquid, they can also depends that how it flows. But if we think about the superfluid, so there is no viscosity at all. So then you can see they can flow around. That is, there is a picture. So it is like a fountain. So that means if you are those who are doing low temperature physics, they know if you just look at helium through a glass cryostat, that means you have a glass cryostat, inside you have liquid helium, it is boiling. And then the moment you decrease the temperature, you reduce the pressure. Basically, there is some vapor pressure on the top of the helium. Then you take all this this air or the particle, the liquid helium, the vapor outside. Then it takes the vapor pressure away. That means it takes the heat away from the system. Then it cools down. And when it cools down, there is one particular temperature. It is called 2.17 Kelvin. The helium becomes. It is really. If you just see, it is very fascinating. Those who are interested, then you can see also later on in the YouTube link the superfluid helium. Then helium looks like a very cool, calm. It is like a very kind of mirror kind of things. Very otherwise it normally it also boils, low temperature boiling. And now if you do some, if you see that also people did a lot of experiment, then you can see all this kind of fountain effect. So that means they can free to move wherever they want. There is no barrier. So that means you can, and there are very interesting field, and Lev Landau from Russia actually he got the Nobel Prize also in superfluidity by doing theoretical prediction, and that's why subsequent Nobel Prize also given in 2003 and also in 1996 because of this. So that means there are different phases which you cannot see at room temperature because of different problem temperature and all these things. But those downstream you can see only at low temperature. And that's why those things are very fascinating. Sometimes that's why people try to understand whether we can see those kind of phases in somehow by means of room temperature. Not every case is possible, but sometimes it is people are trying to do. So now next example which I give you here, that is another fascinating property. I'm sorry that I couldn't do the presentation mode because some issues, but I just put my mouse here and there. So this is superconductivity. And that is also very very fascinating subject. Another kind of phase transition where you can go to from one phase to another phase. So now we start with the Ohm's law that we know from our school days. We calculate the voltage is proportional to the resistance and or the current, and with some proportionality constants in the resistance. And what is the resistance? What is the microscopic origin? How do you do it? And that one is to understand how it is done. So, for example, if you do a measure a resistance, normally you can just apply a current or apply a voltage, then you measure resistance. Or you can, there are flow probes, you can have, there are certain advantages and disadvantages. You can have two probes also, like you can have a multimeter, like as you know, in the go to a lab and then measure the multimeter, two probes, you can measure also resistance. But there are certain advantages in the two probe and four probes. Namely, at the four probe, you can see here you have current, we apply both the ends. And then you can think of when the current is flowing. Current is flowing means the flow of charge basically. And when the flow of charge it is flowing through your sample, then you have point A where you measure the voltage, and you have point B where also you measure the voltage, the potential later on. And later on you calculate while going the electron from one side to another side of the material, how much potential actually changes from this point to that point. So so that means, so what does it mean? So that means the potential, it's the difference. That's why we call it potential difference. So is there a message? No, madam. I'm only with the computer. There is no phone in my side. So here the thing is that, so where you can change the current. So that means why the potential is lost actually. Why the potential? Why we call the potential difference? So that we need to understand. That means while electron is carrying the charge or the current from one side to another side, it finds some disturbances. So when the disturbances, what kind of disturbances? So in a system, you know, there are electrons normally, but there are also some other things. It's called phonons. That means electron can sit also different lattices. That means we call it. They have certain places in the material where they can sit. It's called lattice. Like you can think of in a bus. If you are traveling with a bus, there is some allocated space. So you can go and you can think yourself as electron. So you can go and occupy those particular seats. So it is like electron also distributes in the lattice. And the lattice, when the lattice there is a vibration that is called the quantized vibration. From the quantum mechanics, it calls the lattice vibration. So when the electron goes, they fight each other, they can collide each other. And they can also collide with the lattice. And in the system, if you have some defects, like impurity, and if you have magnetic system, magnetic impurity, they all collide each other. And due to this collision, different things, so they lose their energy, so to say. And that is the reason, that is the microscopic origin of resistance. So that means, or you can think of, I give you another example. Like in you are, let's say, running or working in highway, or you are driving in highway at late night or very early in the morning, where there is less traffic. So that means you can drive fast, there is very less disturbance. But as time goes in the daytime or something in the office hours, where there are many people on the road, they're driving, then if you want to go from place 1 to place B, then you have to, there are a lot of traffic, so that means you have a lot of hurdles in between, a lot of resistance in that case. So one can also correlate that direction. So that means in the different, these obstacles, or you can call it different scattering mechanism. The moment you hit to the other one, then the electron, they scatter. So then one is to take into account all the scattering mechanism, and then you get the resistance. Now the thing is that, so now if you can think the power, at home we keep the electricity bill every month, and like with the power is calculated is I times B, or you can write in I square R or V square by R. So now you think of this I square R, so that means you have certain amount of current you apply to the material. If the resistance, you have some resistance because all the wires we use at home and all these things, copper wire, all these things, then you have some resistance, and then you some current, actually the power dissipates. So that means you have, that's why the dissipates you calculate in terms of watt. Now the question you can ask, if the resistance is zero, if the resistance in some case you can, or not zero at the right moment, you can reduce in some sense. If the resistance you can reduce, then the overall power consumption will be less. So that means we have to pay less power. So that's why in the left hand side you can see a figure where the resistance has been measured as a function of temperature. So suddenly you see that is the original measurement which is done in by the Dutch physicist, the World actually, by Camerlins Owens in 1911, where they found the mercury, Hg. And then if you decrease the temperature, this is naturally the temperature, the resistance drops in metal, because metals give a lot of free electrons. And when you decrease the temperature, that means they also move a bit slower. So that move a bit slower means they can also less chance of colliding. So they can, if you have high temperature, then they're moving fast and they can collide, or they can fight, they can scatter much faster. If you decrease the temperature, there also again the scattering rate is less, and then the resistance also is lower if you decrease the temperature. But suddenly at 4.2 Kelvin, it happens that suddenly the resistance simply vanishes. And then it is really a spectacular experiment, but initially when Camerlin Owens was setting that in his laboratory, actually the experiment was done by the students, and initially he didn't believe. He thought normally in the laboratory students are doing some mistake probably, or there's some instrument error, or maybe some device error, that's why you suddenly the resistance vanishes. He didn't believe. So in experiment what we do, so normally you have to repeat the experiment multiple times, so that if you can tell that it's intrinsic. Then apparently it turns out always do the experiment and always it is dropping. Then they found out actually it is a real thing, the resistance is getting zero, and then you can do a very simple measurement, then you can again apply current, then there is no voltage drop. So that means your resistance is zero. So you can think I equal to V by R, so that means V is no voltage drop. So that means you send a current to the sample, and there is no disturbance. Electron can carry the current from one end to the other end without having any dissipation. Now you can correlate yourself the example which I have given. So as temperature is low, then there is no scattering, they're not fighting each other, they kind of a happy state where they're not hitting each other. Although there is some theory which I will tell you later on, then that is a very fascinating thing. The resistance is zero. That is one of the first thing. The resistance is really zero. That means you don't need to have any power here. So that means the power is goes to zero. And now you can think of now if one can discover such thing at room temperature, then you don't need to pay any electric bills. So that means that would be a revolution in the society. And how revolution now you can imagine for your everyday day-to-day life, that days you don't have any current, let's say how disaster actually at home or anywhere. And now if there is power, you can identify or you can discover certain materials where there is no loss in no resistance is zero, no loss in power, then that can be a huge revolution. So that already you can see 1911, already 100 years over actually. And then people try to understand how to tune those materials where we can go to room temperature. Before that, I can tell you how one measures such resistance. You can say that is a real sample contact. You can see. So that is a really small sample. It is roughly of the order of, let's say, a millimeter, 1.6 millimeter. And then you can see how the contacts are done. So two for current leads and two for voltage leads. And there's also subsequent for the low temperature, there are also Nobel prizes are given 2 times, and for the superconductivity it's multiple times, in fact, because initially we knew that something is happening, but we didn't understand what is the microscopic mechanism to that. But till now, also till today, we understand to some extent, but not fully. If we could understand fully, then we could invent the room temperature superconductor. But still, we are a bit far away from that one. That also I will explain after. Now, another interesting property of the superconductor, that is also fascinating. So one is the resistance zero. Another thing is that, so it is a diamagnet. So diamagnet means if we from movies or college also we know that if we apply the magnetic susceptibility defined by time, and then it is defined by how the magnetization. So that means electron equal magnet. So magnetic moment and magnetic moment per unit volume is capital M. It's called magnetization. And if we apply the magnetization, how the if we apply magnetic field to the system, then how the magnetization changes. That tells you different kind of magnet. But when this, if we apply magnetic field, if your magnetic moment they somehow opposes, so that's why you have a minus sign here. And that particular property is called diamagnet. Normally, each and every material will have a diamagnetism, but which is very small, negligible amount. But if you take a superconductor, it is called a perfect diamagnet. It's called perfect diamagnet because it goes to really minus 1. So you have magnetic field, and it's proportional to the minus of M magnetization. So that, or M by H equal to minus 1. Then you can plot a graph. It should be a linear graph with a negative slope. Now, then why it is important? So that means there is a measurement. It's a magnetizing measure as a function of temperature. So, and the lead, this is measured on lead PV, and the lead is also a superconductor with a superconducting transition temperature is 7.2 Kelvin. Now, if you are above the transition temperature where it is not superconductor, then if you apply magnetic field, the magnetic field all goes through the material. You see all magnetic field, this is your substance, the blue one, and then magnetic field lines are all going through the
ముందే ఎక్కడ వస్తుంది అన్ని యూజ్ చేసా నేను మనం మాట్లాడిన కాన్వర్సేషన్ క్లియర్ 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 క్లియర్. ఇప్పుడు క్లియర్.
ఎక్కడ ప్రాబ్లమ్? ఎక్కడ పెట్టావు ఆన్లో? అన్ని మ్యూట్లో పెట్టాను అన్నాడు. వచ్చినప్పుడు మ్యూట్లో పెట్టాను అందుకని ఆయన దగ్గర
ఇదిగో ఇదిగో
చూసిన
ఇది మ్యూట్, అన్ని మ్యూట్ లో ఉన్నాయి. అంతే ఇప్పుడు
ప్రాబ్లమ్స్ చూస్తా. హలో చేశారు బాగా ఉంటుంది చూడు. బాగుంటుంది. యూట్యూబ్ డిస్ప్లేస్ డబ్బులు తినేది అందుకే కాదు. చేసేది డబ్బులు తింటూ
టీ లేదు కాఫీ లేదు ఇక్కడ. ఏ పిచ్చరు బిందు మాధవ్ మేడం గారు కూలే. ఆయన రూమ్ కూడా రీసౌండ్ వస్తుంది మాట్లాడుతున్నారు. మేడం గారు మధ్యాహ్నం నుంచి ఇంటి దగ్గర చదవాలి. నో వాయిస్ వాళ్ళ దగ్గర అందరూ వస్తున్నారా ఇప్పుడు మీకు ఎవరు కదా సార్ నో వాయిస్
And people also describe in terms of two fluid model. Two fluid means here an normal fluid and super fluid or superconductor. That is also two different kind of fluid. So that is also a very popular theory in physics. People study in different contexts, but in that context also people study in terms of superconductivity as well. Now coming back to the application, so that superconductor, you can see there is also another example. So where you can have let's say different magnets. Now which talk about the magnets means normal electromagnet, which you know, where we can have let's say you apply a current and then the current flows to this one and you create the magnetic field, the electromagnet. But if you can think of, if you have a superconducting magnet, where you have the material is made of superconductor, and those superconductor, then you understand you don't need to apply the current all the time. You apply the current at the beginning, and then those currents persist. So that means you don't need to save a lot of energy in that way. So that is superconducting magnet, and that is some kind of structure of the superconducting magnet at the bottom here. And then if you want to have a magnetic field and you put your sample inside, that is a kind of insert, or where you put your sample, then you put it inside here, and then it goes. So the skeleton actually of a cryostat. There's a skeleton inside, how it looks like. Then we have to develop certain system. Then we have to open everything. Then as a nice picture, so you can see how the superconducting magnets. Another interesting thing people use, you might hear the LHC at Switzerland. There's a Large Hadron Collider, where they have a lot of collider in Switzerland. It's a big project in the France and French and Switzerland border, around 27 kilometers. They have these accelerators or the colliders, where they try to find new materials basically, or new particles. Or one of the invention, maybe you know this large the Higgs boson, which invented a couple of years back, and the Nobel Prize was given. So there it is in CERN. The main center is CERN, Switzerland. And there you can see all the magnets also they use, because sometimes if you want to tune the particular how the deflection happens, and if you want to track, you want to follow their movement, then you can also use the magnetic field over there. So that means magnetic field somehow can tune, because it's kind of a huge 27 kilometers, you can understand, below the tunnel. And they use also in fact the superconducting magnets. Now you can imagine that superconducting magnets are so powerful because you save a lot of amount of energy because of the superconducting the material. And there the magnetic field they use of the order of 4 Tesla, not much, 4 Tesla. And then 4 Tesla is of the order of 1 Tesla is of the order of 10,000 Oersted or Gauss. And then that way you can also trace how the particle moves along the path. So there is also another big applications. Another applications we know the MRI machine, the magnetic resonance imaging, where you know about the tissues and all these things. You get a better nowadays. You go, if you have some fracture or some ligament injury, then you go to doctor, they take the MRI images, and then you can see the machine they use also superconducting magnet of the order of field, of the order of magnetic field, they use of the order of 4 to 5 Tesla also here. And then you can see, of course, you have to go inside, so the field is inside, then the trace. So there is also real application to that what people are using. But still it is very expensive, because you have to have this cold environment outside so that the magnet is in the superconducting state. Because if the temperature is above, then you can have normal state, then you lost or you lose the superconducting properties. Now coming back here, so in another transport system, you can see another example. So you can there is a demonstration which I did also a couple of times, where you can see below again you have the track, and there is a demonstration. You can think of that as a small vehicle or material which made of mostly superconducting material. So there is a little bit ice because it's cold. That's why you have because you need to be in the low temperature, so that it's superconducting. Then it's floating. You see, there is a gap here. And then you can give a push or give some initial energy, then it moves along actually. Then you don't have any problem along the line. So that means you have again saved the power. Now there is also disadvantage. You have to be very much cautious, precautious, because the magnet you can imagine you have huge amount of power inside the magnet. That means you strictly speaking, you apply initial power to the system, then power stays there. But in case there is some accident, let's say, because you can use a huge power inside and you put initially a lot of current to the system, now there is some disturbances or something happened, this is called quench, the magnet, then a lot of energy immediately tries to release all the energies. And there is some accident happened actually, and it happens actually every now and then, but you have to be very much careful because there is helium inside because of the coolant which cools the magnet to a low temperature. But in case there is some disturbances, that means the huge amount of energy somehow try to release all these things, and huge amount to release in terms of heat, and then when it hits very sudden, then you can see all the helium gets evaporates, and it can be kind of foggy, very cold atmosphere, and it's very, very risky. So one has to be also very much careful. Or if you are working in a system that is a cryostat, inside it's very cool, outside room temperature, then you can also put some, let's say, overpressure valves which can release the valve, or some safety device so that you are safe. Otherwise it can be also very dangerous, because huge amount of liquid immediately evaporates. That means huge pressure generates, and it acts like a bomb actually, because huge amount of energy it creates. So you have to have a proper mechanism or the safety precaution so that you are safe. So what I try to point out that, so one has to be very much careful, or when you work with those particular materials. There are advantages, but certain risks or some safety features always you have to take into account. Now here I will show you one curve. So our main goal is that to find out the room temperature superconductor. So now you can see the y-axis, the temperature I have given in terms of Kelvin, and the x-axis I have given in terms of years. So the first, it's the mercury of the order of 1911, and all these materials started. And there is also a bit of history. So you can see mercury, then you have lead, NB, and then people try to see how the TC increases over the years. And when there are two materials, you mix some alloy, you make it alloy, then the somehow TC is increasing. So that is y-axis increasing. And now latest there is a improvement. We could get here up to 150 Kelvin. So 150 Kelvin, it is below. It is roughly minus 100 degrees centigrade. Still it is below. But these materials are very much stable, but very difficult to prepare. But after that, we don't know the mechanism here. So that's why we are a little bit away that why we cannot go to room temperature. We have a very good achievement from let's say minus 270 degree to we could come to minus let's say 100 degree. It's quite good, but still we have to go till the room temperature. That's some long way to go. And very recently, in this year, in fact, in 2020, published in Nature and a couple of physical regulators, where people also claim a 250 Kelvin superconductor, where the TC is 250 Kelvin. So already we are very close, like 25. But there you have to have very high pressure you have to involve. So that means it is not zero pressure, but you have to apply also pressure. Pressure is another medium. So temperature and pressure, both things works. But without pressure, it doesn't work. Without pressure, you can go to minus 100 Kelvin. Now, the moment I was talking why this low temperature experiments also a bit expensive. Of course, there is a bit goal. Once this implemented room temperature, then you can do all the technology immediately comes in, and then you can do all this your. Again, there is a problem. I suppose the screen. Let me. I resume. So I hope it is visible again, the screen. Yeah, good. So here, so I try to give you some brief idea about how these low temperature experiments are also very expensive, because in one sense you may think why the coolant, the helium we talked about, it's expensive, but how expensive they are. So if you think about, I put in terms of euro, and you can also convert immediately. 1 euro is equal to 85 rupees nowadays. So now you can think that 1 liter of liquid helium, which is very cheap, of course, outside you have plenty of percentage, around 70% nitrogen, so we can cool very easily, so that it's very cheap actually, like 50 cent, which is of the order of 40 rupees or something 1 liter. Very cheap. But now talk about helium-4, which is 10 euro. 10 euro means of the order of 800 or 1000 rupees, let's say, per liter. So, and to perform one experiment, you need sometimes a couple of 100 liters or 100 liters helium you need, or it depends what kind of experiment. If you want to apply magnetic field, initially you need a bit more helium. So that means it's also a bit expensive. Now the question asks, okay, people ask when you write about the funding issue and funding agency, then ask, okay, you need so much money. Then you have to also justify, okay, you need so much money, but the goal is different. And the goal you can, at someday you can invest some money, but you have a better prospect in society. So in that way, you have to live with this. But if you just come with the helium-3, where the isotope that is inexpensive, you can see for 4,000 euro, which is really expensive. There are certain experiments also people try to do this kind of experiment also with helium-3, but one has to be also very much careful. So normally once you do the helium experiment with helium-4 or helium-3, we try to recover. So that means when it evaporates from your cryostat, then we try to keep in a big balloon. But the balloon, you have to, it's a light gas, and balloons will go out. So you have to hold the balloon in a closed room, and then you try to compress this one, you pressurize, then it becomes liquid, and you use it, basically recycle. Whereas nitrogen, you don't need to care much, because it is you can get it rather easily. Okay, so now so that is a bit of a superconductivity. That's an interesting phase. Now we come back to the last topic, which is magnetic phase transitions. So where we can think of how it is done. So that means you can see. So you have, as I mentioned, again the concept is there. So you have how the electron sits. You can think of as a bus you are sitting. So that means you have a allocated seat, and electron comes. So this up arrow is given by let's say electron, and electron has a spin, and then that is electron spin. To understand electron spin, you have to go to also a bit quantum mechanics, because spins again you can think of it is in terms of a angular momentum. And now if you can ask, it is not like normal classical fields, like somebody is let's say ball you give a, or a top you give a spin. It is not like that, because I ask you a question or I ask myself a question. So if you have a classical object, you spin. But now if you have a point object, let's say if you just an object, if you top, you just squeeze it to a point, then how these spins you can define classically? You cannot, because if a point object, you don't know which way it is spinning. You don't know. So there comes the quantum mechanics, and the famous example, as you know, the Standard experiment, where they try to find. Earlier we used to know that you have the orbital and then orbital angular momentum, and then if you do the experiment, after that you see the total contribution which you get from the experiment. You will be more than what you expect from. If you take into account only the orbital angular momentum, then it was concluded that okay, the another amount of another which you cannot explain, the total orbital momentum. Another part is due to the spin. It is just name, and it is some sort of also again angular momentum. And then the spin is when you talk about spins. That spin can have also up spin or down spin. And you can think of also it is going, if you have magnetic field you apply, whether it is going parallel to that or anti-parallel. So it is like clockwise or anti-clockwise. So now in a magnet, so when you know the spin, and that spin is so to say, when you talk about magnetism, although the ferromagnet, which you know from iron for a long time back, but this is also ferromagnet, but the microscopic mechanism was understood only because of quantum mechanics, because you understand the spin, and when the spin you understand the spin angular momentum, and then we can describe all the magnetization or magnetic susceptibility, and then only we can try to come what is let's say a ferromagnet. Let's say when the spins are somehow try to align each other in all parallel direction. We see one parallel, all parallel. then it's called a ferromagnet. And the red dotted lines, which is given here, they are some sort of, you can say, is kind of an a lattice where they can see. So the lattice can be also different. It is square lattice, it looks like square, and sometimes they can be also different. So lattice can be also square, lattice can be also triangular. I'll give you some examples of that. But now there is another type of magnets, and earlier we used to think that the ferromagnet is a very common phenomenon in nature. But apparently it is not. If you just, although we know the magnet, iron, all these things very common. But if you just look at the next figure here, the lower part, where the next spins, they are somehow anti-parallel. So one is up, then next is down. One is up, next is down. One is up, next is down. So these are called anti-ferromagnet. Name suggests that they is called anti-ferromagnet. But in nature, if you look it up in the literature and all these things, actually most magnets are basically an anti-ferromagnet, and which is more fascinating than the ferromagnet actually. So if you look at their properties, look at their ground state and other physical properties, and they're mostly studies. Although ferromagnet also interesting, I'm not saying they're not interesting, but there are also many interesting features also belongs to the anti-ferromagnet, and which is also very interesting. And these are, I don't know how this electron, this is, of course, there is Hund's rule and all these things, how they distribute. There, of course, if you have the magnet, which you know, you should have a partially D cell or F cell, so that you can have, again, PPT was some problem. I'm sorry, there's some problem in the PPT, so I think it is back again. So the thing is that, so that means we are again in the different, so we can tune. So there is also that magnetism we can also tune. Like you can apply magnetic field, then you go to its ground state, you can go to different state. And then another property which I want to tell, again I take a ground state here, all these square lattice here. And then you can, there are certain materials, there is also another type of installation, not magnet, but you can have also metal insulator. So normally metal, as I mentioned, so normally metal you have a lot of free electrons, so they can conduct, let's say, electricity, they can carry your electrons, or you can think in terms of band field solids. So that means you have a valence band and the conduction band, so you can have a conduction, and then you have an empty conduction band, and there is a gap so that electron can go easily from valence band to the conduction band and conducts electricity. But there are insulator, which there is a big gap at the band gap, so where the electrons, they cannot take energy from the valence band to the conduction band because there is a big barrier. So that means they cannot conduct electricity. That's why we call it insulator, and then call it band insulator. That's because due to the band gap. But there are certain materials which is very interesting. There is a name to the very British scientist called Mott. And then what he did actually, he first gave a theory that one material can be as a metal, or one can tune to an insulator if you just change the temperature. So that same material can be you can use as a metal, or you can use as an insulator. And that is called a Mott transition or metal insulator transition. And how it happens, I give you a cartoon picture here. So again, you have start with the anti-ferromagnet, one spin up, one spin down, one spin up, and so on. And now the theory says it's called Hubbard model because when the electron moves from one place to another place, it's called T, the kinetic energy. So that means they carry the energy. But again, you have to think also the system. There are, when the two electrons come closer here, you have to have also the Coulomb repulsion. That means two electrons are negatively charged. And then you have to take into account the Pauli exclusion principle. That means two electrons should not have same quantum numbers. That means that's why one electron is going up spin, and the down spin. And then you have to take into account the Pauli exclusion principle. And if the Coulomb repulsion is very, very, so when the T is very, very larger, or here T is very, very larger, when that means the T you can take the electron from one side to another side. Compared to the Coulomb repulsion, then you are in the metallic state, so that means they can conduct the delocalized. The delocalized means the mobile electrons, they can carry the current from one state to the other state. But in other case, when there are T and U, when there is a U, the Coulomb repulsion, there is very strong. So that means two electrons from here and here, they hate each other, or they're very kind of, they're enemy, so they don't let you in closer. They are the repulsion is very strong, that means you cannot move. So they are somehow stuck, that you can call it a localized state. So that is called a mode insulation. So, but this can also you can tune. So like if you have a pressure in a system, like as you can think of in terms of your pressure cooker, like your rice boils or your anything boils, cooks faster. Some materials also you can put here, temperature you can see, if you apply pressure, the same material you can tune to insulator to even metal or even a superconductor. Same material, you can, sometimes they can give a metal so they can hop very easily, and sometimes there is some mechanism where you can also put that they make again a pair, so that means the superconductor. So that means you can also have phase transitions, and happens, then you can tune from one phase to another phase. So that means you can take the same material, you can go to the metallic phase, you can go to the insulating phase, you can go to the superconducting phase, and a lot of varieties of things. But again, the condition is that depends on the material, what are the pressure you need, what is the temperature you need. So the energy scales are different, and depends on the materials, depend on their interactions and all these things. Now coming back to the again to continue the magnetic system, how do we characterize, or when if you have a magnet, if somebody is giving you a magnet, you have to know what is its diamagnet or paramagnet or ferromagnet, that you know. It depends on the spin configuration, whether it's parallel, antiparallel, or if it's a paramagnet, they're a bit chaotic basically. So they don't have a particular order, but they can go whatever they like. So that is called a Curie law. So that means again you measure the magnetic susceptibility, which is the ratio between magnetization and field, and which is nothing but it follows 1/T. So that means if you see here the curve, the Curie law, if you are coming with a paramagnet at some point, the moment you have transition temperature Tc comes, then it becomes, let's say, ferromagnet or anti-ferromagnet and so on. But when you have spins, then when you have interaction between the spins, and then the Curie law modifies to called Curie-Weiss law, then is the theta Tw is another energy scale, and that theta Tw basically tells you whether it's a ferromagnet or it's an antiferromagnet. So for Curie law gives you the paramagnet thing, which is just 1/T or 1/T kind of behavior. But the moment you make the chi inverse, that means the susceptibility inverse, that means it will be linear, because if you make chi is proportional to 1/T, but when chi inverse it's proportional to T, just inverse you take, then it's a linear, it's easy representation. Now there are, if you measure, if you want to know it's a ferromagnet, antiferromagnet, then you try to know how the interaction between the spins. And of course you can see, you can also understand when it is at high temperature, that means they don't have a special preference of order. That means they're in the paramagnetic regime. Here they're all same. But when the interactions they are more prominent if you reduce the temperature. That means the thermal energy is somehow out from the system, or you just remove the thermal energy. Then you can come with the lower temperature, where because of this theta Cw, then try to order ferromagnetically. When the magnetic moment all are spin up, that means magnetic moment is sum them up, then you get a huge magnetic moment, or namely the magnetization. Magnetic moment is high, it's proportional to chi. But if they are again anti-ferromagnet, that means one is up, another is down, then it is coming back to the magnetization is somehow decreases. And that you can be also think in terms of that is a chi representation. If you do chi inverse, then it is like that. So it is very easy representation, because the theta Cw, if it's positive, then you call it ferromagnet. If it's negative, it is called antiferromagnet. But it is the same curve. It's a different way of representation. It is chi, and it is in terms of chi inverse. And there are different materials, elemental materials like chromium, manganese, iron, cobalt, nickel. That this chromium and these are antiferromagnet. Tn, that is called also a famous scientist called Nil. Nil, it is negative. It is of the order of T nil here. It is in terms of degree centigrade. And here in the other things, these are all ferromagnet, which is of the order of, like iron, very popularly we know the Tc is of the order of 777 degree centigrade, or roughly of the order of 1000 Kelvin. So that is how we distinguish. Now there is another fascinating phase. It's called it's a new topic, and it's very popular last 10-20 years, and as of today also it is very fascinating. It is called a spin liquid. So we have spins that are now called liquid. But let me explain you. So now it is again, earlier we saw about the square lattice. We told about the phonons, they sit in the squares. Now they sit in a, let's say, a triangle. So where the spin can be up or down, antiferromagnet, you take a ground state as antiferromagnet. Now you think in the third position, how the spins or how the spin orientation should be. If you put it up, then it is fine. Then up means here up, down, and down. It's antiferromagnet. But I have a problem here because you can see in this direction, one is up, one is down. It's ferromagnet. But our condition is that we told the system it should be in the antiferromagnet state. So that means, but if you put it here down instead of up, then means that is fine. Here up, down, that is antiferromagnet. It's very good. But here we have a problem. It's ferromagnet here. So that means the third position, the spin doesn't know what to do. If it's up, then this guy is happy. This is not happy. And if you put it down, then this particular spin, this connection is happy, and it is not happy. So that means it's like a real like scenario. So that means the spin also somehow they get frustrated. So that means it doesn't know what to do. So if you're up, then it's satisfied with one particular friend, but it's down, then another spin or another friend is unhappy. So that frustration leads, and that means you can have a different sorts of configuration. You can do it also there. You can do it also this position. You can do this position, and this is called a six-fold degenerate. So the energy scale should be same, but it depends how you do. Now in a system, you can think of there are these triangles are everywhere in a system. If you take a material, then everywhere system spin doesn't know, it is kind of a fluctuating state. So that means spin doesn't know it's up or down. So there are always kind of fluctuation that gives you fluctuation. And that means system doesn't order for long run. So that is called a spin liquid. So the spin somehow behaves like a liquid, kind of disordered state. You can think of. If the system is perfectly aligned, then you can ferromagnet, antiferromagnet. But in this case, system doesn't know how to order. So that's why there is a big, famous theory by Paul Anderson, who got Nobel Prize in or who invented the theory around 1973, and he got also Nobel Prize for this one. And there he claimed first about this transition. It's called the first name is called spin liquid, and that liquid basically one can transform to a quantum configuration. Now we are thinking about or it's called quantum spin liquid because the spin values are like spin half we talk about, and then people can use as a quantum computation because nowadays we think about all this classical computer where the represented by 0 or 1, but here you can think of in terms of qubit where you can the efficiency is much higher. And there are certain advantages for this because you incorporate the quantum principles like the superposition principles, and there is a long-term entanglement in the system. That's why there is another beautiful properties of these magnets. Another interesting properties, which is should be the last of my material. Here you can think there is also another material. It's called MnSi. It's called manganese silicide. This one material now you can see they first invented in 1963. Since then, there are 1,262 paper published since then. Just only one material. Now you can interesting how interesting could be one material you invent, then you can be so much interesting. And that is the statistics which are taken in February 9th, 2020 this year, and maybe now it's even more. Now there are also different phases again you can see. So there again, you change the temperature and magnetic field is the magnetic system. Spin they behave very differently. Sometimes you can have a this kind of helical kind of structure. Sometimes you can have a conical. So there are different parts here. This is conical, this range, and the spins will behave like this way. There are spins will behave like this way, and there is paramagnet, and there is another thing is called fluctuation disorder. I'm not going to details all these things, but here my point is that. But very recently, people found last 10 years, they found a new here this red region, and this red region, what is that? And then you can see the spins in this red region, they behave like this one, very peculiar kind of form. So as if there are two types of forms can happen. You can have a kind of a boundary, or it's called topological protected, and inside you have different topics. Sometimes you can in the center, all things it seems that all spins are trying to come to the center here, and there it is off center. And that depends on the different types of mechanism, or you can think in terms of Hamiltonian how the spins are behaving. And this one, if this is in 2D, but if you just think in terms of 3D, then you can see how this one. So that means you have communication from here to here with this particular zone. So this one you can think in terms of 3D, then it comes to this one. And whole material is like this one. And that special name is called fermion lattice. And then means you have some kind of information somehow protected here. And they are highly dense. What is the use? Now all we know the last couple of or 1 or 2 decades, there is this magnetic GMR, giant magnetic resistance, where we have our hard disk and all these things. Earlier, these things would have been very big, but we can condense it to a very small thing so that we can have now all the USB or code. We can have a very high memory, but size is very small. But if this discovers, these are also very close to room temperature now, people have already identified. And if these one now they're trying to actually collaborate with the company so that to apply practical point of view. And this one has the advantage is that these are ultra dense, and then the power which you need very less of the order of a couple of the things which you need for our real hard disk, let's say, which are not portable, which you have to power, let's say, and there it is much faster and much less. So you have kind of low power spintronic devices one can use, and that will be also interesting. And this is another thing also people can think. Now earlier we discussed about the square lattice, we can also discuss about the triangle lattice. Now we can think people, the spins can also sit in the honeycomb lattice, where it looks like a honeycomb. How the spins orientation also different. They can be also in plane. They can, if you took a 3D, then it can be also out of plane. This saddle region. And then also a bit of how the spin orientation basically tells you what kind of order you have in your system. And there can be also different type of magnetic properties. And so till now, what I discussed about the spin orientation and the low temperature or pressure and all these things. Now there are certain techniques also a bit of useful, and like if you want to measure like magnetization, magnetic system, magnetization, you can measure heat capacity, you can measure resistivity to know the resistance. But there are a couple of techniques which we are interested in here in IIT Tirupati. So what we are trying to look at are different techniques, which is we know from our school or college days, but the principle is very simple. Now you can see, we know in the railway tracks, we have a fish plate, there is a gap here. And you know why? Because of the thermal expansion. So when the train comes, then you have the thermal energy, then they expands. So then you have a little gap here so that somehow they compensate. Otherwise you would have an accident actually. So this is somehow what you do. You have a length L, and then you apply some current, some temperature here. Then you have some expansion along the length, and then you can calculate thermal expansion coefficient. But why it is interesting? So that means then we can measure this expansion very precisely by means of a capacitive dialectrometer, and that means you have a parallel plate capacitor here. On the top of you put your sample. Then when the sample changes its length, basically, then your capacitor plate changes the distance. Then your capacitance also changes, and then you can calculate how the thermal expansion coefficient, the thermodynamics or the volume and temperature, also entropy is involved to the pressure, and then you can have your resolution. We are going to very high resolution and angstrom level. How the length changes in the angstrom level you can measure, and how it is done you can look it up in the simple formula. How the length changes is indirectly proportional to that. Again, PPT it is just a moment. So. So again, it is good. The PPT somehow it is, I think, the internet fluctuation. So that means you can have this technique. You can also change as a function of temperature. You can have a field. You can have a pressure. So that means for a magnetic system, also the material which I am studied, which I just talked about, we can also measure such material also as a function of different parameters. But it depends on what kind of temperature you are interested in, what kind of field, what kind of pressure. That means also depends. And this is also another thing which you can do. So this is again thermal expansion. What we measure, try to measure the lattice effect. So that means how the lattice, basically how the crystal, or if you have a sample of ABC axis, so how they are changing. So these are also you can study. You can apply this as a pressure cell. You can put a pressure inside, and then you can see how this lattice, the wavy things are, how they can also compress. Then if you compress, how the effect. So that means the electron, they can also interact with each other more. So that all these tuning parameters you have in your hand, then you can play around. And to sample, sometimes what you study, you can see how the typical sample which you look around. This is a typical sample. This is 1 millimeter paper, and then you can put it. You want to measure the expansion along the direction, and this is the typical rheostat. How does it look like? Sometimes a bit complicated, but the main thing is that you can measure the temperature, pressure, and the quantity which you are interested in, like specific heat or thermal expansion in this particular case. Or there are some commercial instruments you can buy also, and these you can make it homemade instrument. You can design yourself and do the experiment, which is more fun sometimes because for the students' point of view, for learning point of view also. And there are certain other experiments. If you just think about the pressure, this is also superconductor transition of lead, and that you can measure the magnetization under pressure. So that means you have a pressure cell there where you can apply really high pressure. And now I give you some example where 10 GPa means like 10 GPa means like 10 kilobar. So you can think of yourself again the analogy like in your bicycle or whatever, 4 to 6 bar. Now it's kilobar. How strong pressure. So it depends on the material. Some materials you need really high pressure to tune the phase. That you can see. The lead also can be tuned to different phases. This is superconductor transition of lead. And then you can apply pressure like 2 GPa, then you can shift the transition to a lower temperature around 6.5 Kelvin or so. And so that means instead of lead, you can put some other materials which you are interested in, then you can tune on this material, you can go from one phase to another phase. Okay, so with that, I would like to come to a conclusion. So that means what I discussed here basically various exotic phases which you cannot find at room temperature, unfortunately. But the idea is that whether we can go to that particular temperature where we can have those particular phases, and whether we try to understand, we can tune to the room temperature with by means of pressure or magnetic field, and which are having potential applications, and then the engineering actually comes in. And some of the rare techniques which study to those exotic phases, try to understand. And of course, the theory and experiment goes hand in hand. So one has to do also a bit of theory to understand what is the mechanism, so that we understand better. So with that, I would like to finish with acknowledging there is also some funding support from DST, ACIB Science Engineering Research Board, and also some PhD students who are also working in the field. And thank you for giving me the opportunity to present here in this webinar. Thank you very much. If you have any questions, I would like to take questions now, and or if you have questions in email or something, you can also do it. So thank you very much.
Thank you very much, sir, Dr. Rudrasekhar Manna. Really, it was an excellent presentation on phase transitions of magnetic.
As a function of temperature and pressure. I hope this has enhanced the knowledge of the participants regarding these phase transitions. Now, sir, we have a number of questions in the chat box. Can we go through the chat box, sir? See, I'll help you. At 11:26 starting. 11:26, there is one question. 11:26.
Sometimes there is a property wise also in any magnet. There is also a difference in when you go to bulk to nano. From bulk means when you talk about the single crystals and all these things, and when you deposit in a thin film. So there is also properties may change because sometimes you have surface effects and many other things can come in. And in this nanomagnets also there is also superconducting, but sometimes it has to be it has to be consistent, or it has to be reproducible. But how the properties changes, properties, maybe you can increase the TC a bit high and low. That is one difference. And as I mentioned, the surface property is very important, because when you talk about the nano thing, the surface properties change dramatically. So one is to take care all these points. Thank you.
I think another question is at 11:34, sir.
Okay. The same person. Okay. Are the superconducting materials eco-friendly? Yes. So, for example, I don't know what exactly you mean by eco-friendly, but normally these materials, because we are never fortunate to have the room temperature superconductor. But for example, superconductor I have here. Like sometimes if you think of lead is a little bit poisonous in this material. But if you think about the IPCO, which is the high temperature superconductor, yttrium, barium, copper oxide, which is after doping you can go to 150 Kelvin. And there it is actually no problem. So it is a room temperature, it is kind of metallic, and if you cool it down, it becomes superconductor. So at room temperature is eco-friendly, no problem. But of course, if you try to make a material for real purpose, one has to take into account whether it is, as I mentioned, if you have pure lead or something is there. In fact, if you look at the periodic table, almost all the materials are superconducting. But of course, it depends on the temperature and pressure. And sometimes they become very low temperature superconductor. Sometimes it is you need to apply really high pressure to become superconductor. So it depends on the material properties. So if it's really at room temperature, one has to see also chemistry point of view, how eco-friendly they are actually. So that is also a good question, but it depends actually what kind of composition you are looking at. But IPCO point of view, where yttrium, barium, copper oxide is absolutely fine. So we work with bare hand and we can do experiment, no problem. But they are still in their metallic state, because room temperature, when we make the contacts and on all these things, is room temperature, so no problem. But superconductor, what happens? So that we don't know, because we have to go again to the low temperature. But I don't think that is a major issue. But if some materials are there in that direction, some hazardous or dangerous compounds, then one is to be a bit more careful. Yeah, thank you. Any other question? 11:42.
Sir, there is another question. It's 11:42.
Correct. Yeah. So what is the meaning of phase transition in the AC susceptibility? So AC susceptibility, the basic difference is that normally DC susceptibility, where the field doesn't have a frequency dependence, and AC susceptibility is that you apply a magnetic field. That's why you have a primary coil and you have secondary coil, and you have a frequency. So I think for superconducting material, it is as of my knowledge. So what I know, it is not very much interesting. So because you can see again the similar kind of pattern, the diamagnetism. That means because in superconductor, what you are looking at, you try to expel the total magnetic field which is inside the material. So in that point of view, it is fine. But the moment you are looking at spin glass system, for example, where there's an impurity, spins are somehow sitting in the impurity, then it matters. So then matters AC susceptibility. You have to see how as a function of frequencies, how the phase transition, whether shifting and all these things, that is a clear signature of the AC susceptibility. Yeah. Thank you.
There's another question at 11:55, sir. Just I am taking the questions from which were posted in a YouTube channel. I'm copying them here, sir. That is. These are all the questions from the YouTube channel.
Yeah. So at 11:55, let me read. So at superconductivity existing at room temperature, then what is the use of again exactly that is a good question. That is I was trying to even discuss. So you see, first of all, it is a phenomenon. It's a very different property. It's an interesting property. Both property in terms of resistance and in terms of the diamagnetic effect or the Meissner effect, the levitation effect actually. So you see, there are certain observations that is actually a philosophy that we see at room temperature. But our idea is that how to raise the temperature so that we can go to the room temperature. And what people are trying to do over the years, you see, we could go to even a very good progress like 150 Kelvin. So that is the goal. What we are trying to do, we are trying to raise the room temperature so that one can use practically. I mean, at moment also you can use actually at like minus let's say 100 degree or minus nitrogen temperature. Let's say nitrogen is very cheap, you can use, but still you have to one has to be a bit more careful. All the devices has to be at low temperature and all these things. It's a problem. But ultimate goal is that direction. Now we can think of also in that the electricity didn't invent in one day, so it took some time actually to discover. And when it is discovered, then it takes some time. So basic science is like that. So sometimes there are fascinating properties, and like you can think of also superfluidity. Superfluidity also, then you one can ask, okay, what is the use of? But still, we try to get to know that how the material behaves and what is the different phases. And there are also people talked about the bosons and condensation, for example, and those kind of essential things which we try to also understand the basic physics. And application point of view, still I think we have to wait a bit, and so that it is at room temperature, then we go for applications. Okay, thank you. So any other questions? I think at 12:1, any day-to-day live application of phase diagram. The phase diagram live application, you take water. Water is the best example. We can do every day. I mean, you boil your water, then it goes to another phases, and or in ice, just put in your ice cubicles in your big refrigerator, or anything can be also added in the direction. Yeah. Is there any other question, madam?
Sir, we have number of questions in YouTube channel.
Okay, okay. Acha,
I'm
there.
collecting them. So, sir, if you don't mind, if can you share your email ID to them, sir, so that they can
Yes, sure. Actually,
they
it's in
can
our
reach you through email.
correct. It's in our web page actually in IIT Tirupati. So you can look it up. Should I
It
write
will
it
be
here?
useful for them if you type that in the chat box, sir.
Chat box. Okay.
Yes, sir. Absolutely.
Yeah. Okay, I have typed already there.
Yes.
Yes, and they can also look it up in the web page also. There also they find similar information.
Yes, sir. Okay, thank you. I'll ask the participants to post your questions to Dr. Rudrasekhar Manna. He is from one of the prestigious institutions of India, IIT Tirupati, from Department of Physics. Now, let us conclude the session here. Thank you, sir. Thank you very much. Even though you have a very tight schedule with IIT Tirupati and regarding the PhD interviews and evaluation, MSc evaluation processes.
Really, I'm very thankful to you for giving me the valuable time to share your knowledge with all of our participants. Sir. Thank you very much. Sir. Thank you, sir. We all are fortunate to have you with our session, sir. Thank you very much. Dear participants, feedback has been posted in the chat box. Please fill it and Please take care of yourself. Be well. Keep learning. And we will meet again at exactly 3:30 in the afternoon session. Thank you. Thank you.
రైట్. లంచ్ ఏంటి? మీదే మా ప్రాప్తం ఉన్నాం మనం.
Okay.
మేడం చూడండి, మీకు ఎంత ఫుల్ కవరేజ్ ఇచ్చాం. మెయిన్ వెబ్సైట్లో కూడా పెట్టాము. ఇంకా రేపు కల్లా నాకు ఏం చేస్తారు నాకు
Don't delete
500 వీస్కి వెళ్ళాలి. అది 300
మీకు ఎన్నో స్టార్టింగ్ లో మేము చపాతీ లేదు, టీ లేదు, కాఫీ లేదు అని అందరూ ప్రిన్సిపల్ గారు వాళ్ళందరూ ఇనే ఉంటారు. మరి
నీ వయసు
వాళ్ళందరూ ఉన్నారు ఆన్లైన్లోనే.
సరే ఇప్పుడు
డోంట్ సైన్ అప్ అంట, ఉండండి కాసేపు. డోంట్ సైన్ అప్ అంటున్నాడు నరేష్ బాబు. మరి ఏం లేదన్న కావాలి. డోంట్ డిలీట్ మీట్, వెయిట్ ఫర్ 15 minutes. ఇట్ ఈస్ రికార్డింగ్.
12:30 ఆపి, ఇప్పుడు రికార్డింగ్ ఆపమంటే ఆపుతా.
అంతండి రికార్డింగ్. ఏమో రికార్డింగ్ ఏమో
మనకు తెలియదు అవన్నీ ఆశ్చర్య సుధాకర్ గారు చూడాల్సి. బాక్స్ ఇచ్చారు
నేనేం చాలా అదే ఇప్పుడు మనం మాట్లాడుకునే వస్తున్నాయంట, ఇంట్లో పెట్టలేదు. ఇప్పుడు నేను మాట్లాడే వస్తున్నాయంట నరేష్.
ఎక్కడ వస్తాయి మేడం అసలు?